Greetings from another Chem-A. Mr. Picard's lockdown. No, it's not exactly lockdown. Well, stay home and stay safe. And if you do go out, social distance is appropriate, and a mask certainly appropriate if you are going to a more crowded space to keep yourself healthy and other people as well. This week we're going to continue and take a look at the reaction we did last week. Last week we combusted hydrogen and with oxygen and made water, and that is a chemical reaction. We took hydrogen and added some oxygen, and what we ended up with after the reaction was indeed water. And what I've just written out is in fact a chemical equation of sorts. It represents what happened in the reaction. We had atoms of hydrogen combining with atoms of oxygen to form water. It doesn't give us a lot more information about how much hydrogen we used or how much oxygen, even what form it is. It turns out that hydrogen and oxygen come in slightly different forms when it can bond to itself. And of course, what is water really made out of? But nevertheless, this is the reaction. And for the reaction itself, we actually don't use an equal sign, but we use this arrow, and we actually got a little bit of heat, light, energy released. So let's take a look at a chemical equation for this reaction. And so I'm going to put down this definition, which should be a review at this point for you, but it's in the terms and vocabulary words that I posted. And what is a chemical equation? It's a way to represent a chemical reaction using chemical formula and chemical symbols. And it's more precise than just using words like I did before. And so let's take a look at that in a little more detail and what that means. Okay, and I'll write down the chemical formula that we used, or represents the reaction we did last week. We actually took some hydrogen, but we took two of them. And I'll talk about the subscript next in a moment. And we added those to O2. And we actually had a doubled amount of H2. So we put the big 2 in front. That's called a coefficient. I'm going to show you that definition in a moment. It also is on the vocab term list. Then it yields or goes through a reaction. We don't use an equal sign, we use an arrow. And we actually end up with 2 parts of water, 2 molecules of water. And so that is actually the balanced chemical equation for the reaction that produces water. We call that reaction, happen to call that reaction combustion. Let's break it down a little bit for you about what these numbers and the symbols already, what they mean. One thing is the symbol in the middle is called a yield sign. A yield or yields sign, meaning that it gives up or produces water. So these two substances, when they come together, we use a plus sign for that, yields 2 parts of water, H2O. And it means it's a little bit different than a yield sign, I suppose, that on the streets, like stop signs, yield signs. But in fact, when you see that yellow sign, you have to yield or give up your right of way to cross that road. So it's giving something up. This is giving up water. So we have another important term, again, a bit of a review perhaps, and that's this one, chemical formula. And that applies to an individual substance, whether that substance is a simple one like hydrogen or a little more complicated like water, or maybe it's very complicated like, I don't know, cholesterol or some big organic molecule. But a chemical formula is a combination of symbols and numbers that represent the elements in a compound and their atomic proportion. And so it gets a little more precise. So let's go back and take a look at what that meant in terms of our equation. Well, let's look at two more, another review here. Reactant and product. So reactants is just the word we use for substances that go into a chemical reaction. And it can be a single substance or multiple substances. And the product is what we make. It's the substances or substance formed as a result of a chemical reaction. And sometimes the reactant can be a single one that breaks apart into multiple products. Sometimes the reactants are several, and they make a single product. It doesn't have to be singular or plural. That's how it works. Okay, so reactant and product. But reactants are generally depicted on the left side of the equation, and that's just a convention. We just usually start with the reactants, and on the left we go through the reaction itself, represented by a yield sign, and we get a product. And we don't use an equal sign because it's not exactly equal. I mean, there's been a change. We want to represent the actual reaction happening with some symbol that's other than equal, because there's been some change. The change hasn't been in the types and numbers of atoms. That's going to remain the same on both sides of this reaction. We demonstrated that with the conservation of mass principle in our last video. But there's, except perhaps a loss or gain of energy of those substances, it's not exactly equal. There's been a change. Earlier this year, we used a substance called ethanol. It's a type of alcohol, and we used it in a lab. I think you might remember the name. And the trouble with that description is it doesn't really tell us what it's made out of, and so it's not as useful in determining what it's going to do in a chemical reaction. We really have to know the chemical formula. You know, what is it made out of? How many atoms of what type of element make it up? So here's you might remember, I think I even showed you this model. Here's a model of ethanol. And the model has white, smaller balls that represent hydrogen in this case. It's got one red, which represents an oxygen atom. And it's got two carbon atoms represented by the black balls. And those colors are conventional in some ways, but they're arbitrary. But you often see those colors for those elements. And you often see hydrogens represented by the smaller size because it's a very small atom with just one proton in it. So ethanol. So the question is, how do we write the chemical formula for any element as it goes into or comes out of a chemical reaction? And we use a counting method, and we also use something called a subscript. And a subscript is a number in a chemical formula that tells us the number of atoms in a molecule or ratio of elements. So how many atoms of hydrogen, how many atoms of oxygen, how many atoms of carbon. And we call that a subscript. And literally that means written below, right? Or below written. Sub below, script is to write. So let's write a chemical formula for ethanol, and we'll use our model to help us here. And I'm going to start with the carbons in the middle. And so the symbol is a big C, of course. and there's two of them, and I'm going to put a subscript 2. There isn't really an exact equivalent in mathematics for this, so it's unique to chemistry, but it means there are 2 carbon atoms in an ethanol molecule. And let's count up the H's first. 1, 2, 3, 4, 5, 6. So H is the symbol, we can get that off the periodic table, of hydrogens, and there were 6. And the remaining unaccounted for atom is O. And there's just one of those. And just like in math, we don't really usually write a 1 down there. It's just assumed that there's 1 if there's no other number. So C2H6O is in fact the chemical formula for ethanol, and it tells us exactly, what's in it. Let's return to a substance that we all know pretty well, and that's water. And I think another thing we know about water is we actually call it quite often by its chemical formula. H2O, right? Everyone knows H2O. You might not have known that it was written in that format with the large H, the subscript small 2 below, followed by the big O. And perhaps the model was not something you would be familiar with too. But there it is. We've got the 2 H's represented in the model by the smaller white balls, H2, there's 2 of them. And there's a single or 1 oxygen, and we don't put a subscript there. It's sort of a waste of time. We're just going to assume that there's a 1. And so that is an accurate chemical formula, complete with subscripts showing that there's 2 hydrogens, for water. But sometimes we do reactions, and we're going to represent them in a chemical equation. And let's say we actually end up making 2 parts of water, or 2 molecules of water. And when that happens, we need to account for that and represent that in our equation. And to do that, we use what's called a coefficient. And a coefficient is a number in front of the chemical formula that tells us how much we have of that particular substance. And it's a large number, and the word coefficient is also found in similar, if not almost identical use in math, pure math, outside of chemistry as well. I can sort of demonstrate that here. So if I wanted to represent both of these parts of water, I would want a nice big 2, and then I'm going to write the formula H2O. And what that means is I have 2 of them. And the 2 is a big coefficient, very different than the small subscript. Small subscript is just kind of saying that there are 2 hydrogens. It's not affecting the O in any way. And yet the large 2 is saying that there are 2 of this entire molecule. I suppose in math, the 2 might come in front like that, and maybe you have an A and a B inside there. And that would, of course, indicate that the 2 is multiplying everything in the parentheses. We don't use that parentheses in chemistry, but it's a similar idea. We're saying that there are 2 molecules of water. And let's do a little bit of a sum up, I think, here. And talk about what we're trying to do here. So a chemical equation is a way to represent the entire chemical reaction. What goes in, what comes out, how much of everything that we need in case we would like to do this again, or even make a prediction about what we get. And we use chemical formulas within chemical equations, and we use other symbols and numbers to make those. What goes into a chemical reaction, I suppose somewhat like the ingredients in a recipe, is called a reactant. And we would represent those with a chemical formula, as well as possibly with a coefficient to measure how much. Product is the same way. It's what we form after the reaction takes place. And either of these could be single substances or multiple. We could make a reaction could produce several products or just one. It could take a reactant might be single and break apart to form many products. We use the equation works either way. So chemical formula represents a particular type of substance. Let's bring back our friend ethanol here, which, is it just me or does ethanol kind of look like a poodle? I've always thought ethanol looked like a poodle. And the formula, at least the model does, I don't think the real molecule does, again is using symbols, same symbols, element symbols that are found in the periodic table of elements, like C for carbon. It uses subscripts, meaning there are two. H is another symbol, hydrogen, 1, 2, 3, 4, 5, 6. And then we have one oxygen. So the chemical formula, again, for ethanol is C2H6. There's no indication of how much here, or the assumption would be we just have one part or one element. We could, of course, have multiple poodles, parts of ethanol. And if we wanted to represent our two poodles, ethanol molecules, we would want to put a large 2 in front. And that would mean multiply everything that follows. It doesn't mean that there's just, this 2 is not just multiplying the C or just the 6 or just the O. It's meaning that there's 2 complete molecules here. And we've covered subscript, I think, already. Coefficient, we've done it.